Have you ever come home to the smell of a warm apple pie or a peach cobbler filling your house? Many of these wonderful fruity aromas come from esters. For example, one of the molecules that makes up the aroma of apples is our ethyl butanoate ester shown here. A lot of these esters are also involved in the fruit flavor. So ethyl butanoate is actually added to orange juice sometimes to add some of that artificial orange flavor to make it taste more fresh and orangey. In addition to their role as scent or flavor molecules, esters also are important in a variety of other biological applications, including as signaling molecules and within our lipids and our cell membranes and our fat cells. Because of these different biological roles, it's very important for us to understand the properties of esters as well as their various reactions. Now, esters, of course, as we've seen, are one of our carboxylic acid derivatives, but of course they vary in their properties compared to carboxylic acids because of that additional carbon that's attached to our oxygen. Right? So we still have our dipoles from our carbons to our oxygens with our partial negative charge of our nucleophilic oxygens and our partial positive charge of our electrophilic carbon. So this means we will have dipole-dipole interactions, but we don't have the hydrogen bonding interactions that we have in our carboxylic acids. Right? So we have no hydrogen bond donors, which means that our esters tend to have more moderate boiling points and melting points without that stronger intermolecular interactions of our hydrogen bonding. We do still have pretty good water solubility generally because, of course, our oxygens are hydrogen bond acceptors, so we can accept hydrogen bonds from our water. We just can't form hydrogen bonds between our esters themselves. These properties, of course, again, directly relate back to some of those biological roles of our esters. Right? Their moderate melting points and boiling points mean that we can have small esters as relatively volatile molecules that can then be a part of those aromas. Their decent water solubility, of course, is very useful in our biological systems where we generally have a high amount of water present, right? So it's often important for our biological molecules to have pretty good water solubility. So both of these, again, connect to that biological role of our esters as well. Now let's take a look at some of the reactions of our esters. Of course, as we've already seen, we can easily form esters through esterification reactions. Esterification reactions take our carboxylic acids, and we do our usual nucleophilic acyl substitution reaction with an alcohol as our nucleophile. We do this in the presence of an acid as our catalyst, and this will create our ester as we combine the carbon chain of our carboxylic acid with the carbon chain of our alcohol. Esters will undergo a lot of different nucleophilic acyl substitution reactions since they are still a carboxylic acid derivative. So all of those reactions that we've looked at previously will apply here for our esters. We can convert them to carboxylic acids or to other carboxylic acid derivatives using those various nucleophilic acyl substitution reactions. One of the more unique ways to form an ester, though, is the Baeyer-Villiger oxidation reaction. Baeyer-Villiger oxidation actually allows us to create an ester from a ketone. So our ketone, of course, has our two carbons on either side. We're going to react this with a peroxy acid. Remember, we've used peroxy acids previously in order to produce epoxides. And a peroxy acid, we have our hydroxy group, but then we also have our two oxygens there, which of course that gives us the single oxygen-oxygen bond that leads to our peroxy name. These are going to react together and create an ester as well as a carboxylic acid. Now, in our overall reaction here, what's happening is essentially we're taking one of our oxygens and just inserting it here within our ketone. So that oxygen ends up becoming our oxygen in our ester here of our product, and our peroxy acid just leads directly to our carboxylic acid product. Here's our peroxy acid, and of course here is our ketone over here on the left. So it's somewhat of an unusual reaction because we're actually kind of temporarily breaking that and inserting a new oxygen here. But it allows us to create very specifically an ester from whatever our ketone structure happens to be. So as an example, if we look at this reaction here of our butanone with our peroxy acid, again we're going to be taking this oxygen here, and you might note, so we could insert it here or here, right? I didn't specify initially where that oxygen is getting placed. And overall this oxygen is going to get inserted next to our larger alkyl group. So it's going to add to the larger carbon chain of our ketone. So in this case, if we put that oxygen right in here, we'll end up with our ester looking like this. We still have our same 4 carbons, just that new oxygen inserted in between the 2 carbons of our larger carbon chain and what was our ketone originally, but it's now the carbonyl of our ester. So this becomes our ethyl ethanoate, and of course our carboxylic acid is just our acetic acid, which is what's left after we remove our single oxygen here of our peroxy acid. Once we've successfully formed our ester, we have a variety of different options for how we can then react that ester functional group to create new functional groups. Of course, I already mentioned our different nucleophilic acyl substitution reactions that would allow us to convert between our ester to our other carboxylic acid derivatives. But we can also go backwards from our ester to our carboxylic acids. One of the most common examples of this is the saponification reaction, which allows us to create soap. So in this reaction, we take our ester, and we're going to react it with a strong base. So we might use sodium hydroxide to create our hydroxide ion. And that base will react with our ester and break it apart or hydrolyze it in order to create our carboxylic acid and our alcohol. Now, since we're using basic conditions, our carboxylic acid is going to get deprotonated to its anionic carboxylate form. And it's that anionic carboxylate that will make the good soap that will then be often used in a lot of our different soap products. This reaction follows our standard nucleophilic acyl substitution mechanism. So with our strong base, we're going to come in and attack our electrophilic carbon here of our ester. Our electrons move up to our oxygen, forming our tetrahedral intermediate. From here we can eliminate our alcohol portion of our ester, our alkoxy group. And we've completed our substitution and added on our new hydroxy group from our hydroxide base. Of course, at the same time as we're doing this, we're creating an alkoxide, which of course is a very strong base itself. And our alkoxide will of course pull off our hydrogen here of our carboxylic acid. Since our carboxylic acid is a weak acid, and this is a very strong base, we'll have an acid-base reaction to lead to our final carboxylate and alcohol products. So in this case we have our butanoate as our carboxylate here, and we have our methanol as our alcohol that formed from our initial methyl butanoate ester. So again, of course, the whole mechanism here, I walked through it quickly just to show you kind of what it looks like in this scenario, but this should be very familiar to you at this point, since it's just following our standard addition and elimination nucleophilic acyl substitution mechanism. I won't go through all of our other possible ester nucleophilic acyl substitution reactions, just because, again, they'll follow that same standard mechanism, which we've already seen in our look at nucleophilic acyl substitution reactions. The next reaction that we'll look at is our organometallic addition to esters. Now, of course, we've already seen organometallic compounds used to react with ketones or aldehydes, right? So we'd often use our Grignard reagent, where we have that magnesium and our halogen there, and this creates a very nucleophilic carbon bond that can then attack our electrophilic carbonyl carbon of our ketone or our aldehyde. Now in this case we're reacting with our ester, and so we have still our carbonyl carbon that's going to be electrophilic that will get attacked by our nucleophile. But the difference here, of course, is that we have our alkoxy group here that can actually act as a leaving group here with our ester that we didn't have with our other carbonyl compounds. So instead of just adding on once with our organometallic compound, we're actually going to add on twice and kick off our alkoxy group here, similar to what we see in our nucleophilic acyl substitution reaction. So normally we'll add our organometallic compound and then follow this up with acid in order to create our substituted alcohol. So we add on our two new carbon chains from our organometallic compounds, and we also, of course, release that alcohol here. And the first step here, of course, we'll want our ether, so we don't have any water there to react with our organometallic compound. And then in the second step, we'll be using acid to again protonate those alkoxides to get to our final alcohol products. Let's take a closer look at our mechanism as we look at the reaction between our propyl magnesium bromide as our organometallic compound and our ethyl ethanoate as our ester here. So again, as we know, our nucleophilic organometallic compound will attack that electrophilic carbon of our carbonyl, and we're going to move our electrons out of the way up onto our oxygen. Right? So far it's looking exactly like our reaction between our organometallic compound and a ketone or an aldehyde. This creates our alkoxide, and we now have added on our carbon chain. That would be the 3 carbons here. I'll highlight those in a different color here just so we can see our carbons that came from our organometallic compound versus the carbons that we already had on our ester. So those are added on here, and notice we again have a tetrahedral intermediate here at our carbonyl carbon. So our next step is actually going to be just the same as in a nucleophilic acyl substitution reaction. We're actually going to kick off our alkoxy leaving group as we bring our electrons back down from our oxygen. So this will then create our carbonyl carbon, and then we have our bond coming over here to our 3 carbons of our organometallic compound. At the same time, of course, our alkoxide is kicked off. This would be our ethoxide in this case from our ethyl group on our ester. Now at this point, right, you might think our reaction is finished, right? We eliminate our group as we do in a nucleophilic acyl substitution reaction. But notice our product here is a ketone, which of course is also very reactive with our organometallic compound. So our organometallic compound is actually going to react again with our ketone. So we bring in a second unit of our organometallic compound. Again, I'll use my orange color here so that we can tell our carbon chains apart. And we'll follow the same mechanism that we used previously for our organometallic reactions. So we tack that electrophilic carbon, move the electrons up to our oxygen, and we create our alkoxide here with, of course, our new bonds to our 3 carbon chains from our organometallic compound. So we've added on 2 3 carbon chains to our original 2 carbons of our ester. And then, of course, that second step with the acid is just going to serve to protonate our compounds to get us to our alcohols. Right, so we bring in acid over here, and we can react with our alkoxide. We protonate our alkoxide to form ethanol, and we'll protonate our tertiary alcohol here. And so our final products in this case, we have our now 6 carbons added on to our initial 2 carbons of our ester, and then of course the other 2 carbons forming our ethanol from the other side of our ester there. So we get a mixture of 2 different alcohols from our original ester. Again, in terms of our mechanism, we're really just following a nucleophilic acyl substitution reaction in the first step. So with that nucleophilic acyl substitution, we see our typical addition, tetrahedral intermediate, and then elimination of our leaving group. After that, we're then reacting again using our organometallic addition to our carbonyl. And we can notice, of course, our reagents here are the same as what we'd use when reacting with a ketone or an aldehyde, right? We always keep it anhydrous initially, no water present so that we don't react with that water with our organometallic compound. We follow that up with acid in order to protonate our alkoxides to produce our final alcohol products. In that last reaction, we saw a lot of similarities between how our carbonyls of our aldehydes and our ketones react compared to our esters. So we also see some similarities in the reduction of our esters compared to the reduction of our other carbonyls. So our esters can be reduced to alcohols similar to our other carbonyls, but they're going to behave more similarly to our carboxylic acids, where we're going to require that strong reducing agent in order to reduce them to our alcohols. So if we start with an ester, we're going to treat it with our lithium aluminum hydride in the same way that we have treated our carboxylic acids. So we add our lithium aluminum hydride, and again we keep this in ether because we don't want that violent reaction between our lithium aluminum hydride and water. And then we follow this up with water or with acid in order to protonate our products to get our final alcohols. This is going to actually break apart our ester and form 2 different alcohols. We'll get a primary alcohol from 1/2 of our ester, and then of course another alcohol on the other side, which the structure there will depend on what the structure of this alkyl branch is of our original ester. Now this reaction, again, shares a lot of similarities with our nucleophilic acyl substitution reactions. Our lithium aluminum hydride essentially acts as a donor of hydride ions, which are negatively charged hydrogens. So we're essentially reacting with our hydrogen. Our hydrogen is acting as our nucleophile here, and it's again attacking our electrophilic carbon and forming that tetrahedral intermediate. So this results in our usual alkoxide We still have our oxygen linked on, and we've added on our new hydrogen here as our nucleophile in this reaction. Again, of course, as always, we can bring our electrons down and kick off our oxygen as our leaving group, and that's what ultimately ends up separating our ester and leading to this other alcohol product. So we're getting two different alcohols, one from the alkyl group of our ester, and the other one, as we'll soon see, is coming from the carbonyl of our ester. Right? So each of these oxygens here are leading to alcohols. Right? So we have alcohol over here that's produced as this breaks off. And of course we're going to create our second alcohol up here as we are reducing this. So that creates our two different alcohol products. So initially what I've shown so far with my mechanism, right, just leads to my aldehyde and my alkoxide. But again, similar to my last reaction, my aldehyde is even more reactive to my strong reducing agent than my original ester. So this is essentially going to react again. We're attacking with another unit of our hydride from our lithium aluminum hydride, and that fully reduces this to form our two alcohols. So our aldehyde is fully reduced to our primary alcohol. We have now our two hydrogens added on as these two different hydrides attacked. One in our first step, one in the second step. This alkoxide gets protonated by our acid here to form our isopropanol from our original isopropyl group of our ester. Again, as you can see here, my alcohol product from my alkyl group on my ester can vary based on what my ester looks like. In this case, I produced a secondary alcohol because, of course, I had my secondary carbon here initially. But the alcohol that I produce from my carbonyl is always going to be a primary alcohol, right? Because our ester itself is always a primary carbon, right? This carbon only has room for one carbon-carbon bond, since the other three bonds are all to oxygens. So what we see here with our esters is that they have some similarities to our carboxylic acids in their reactivity, but they also have some similarities to our carbonyl compounds of our aldehydes and our ketones. Right? So they do a lot of nucleophilic acyl substitution reactions like our other carboxylic acid derivatives. We can use that to convert between those different derivatives there, but we can also react them more like aldehydes and ketones in order to create a variety of different alcohol-based compounds. So in addition to their important biological roles and their ability to link molecules together into larger molecules, our esters also have important roles in our organic synthesis as well.